Today, the SETI talk is about Kepler. It's about a tribute to this amazing space mission. We don't want this to be a sad tribute. We want this to be a positive tribute. I'm just going to say a few personal words about Kepler, the way myself I perceive Kepler, and how great this mission has been, of course. So as you know, NASA announced recently the end of the spacecraft, meaning that the spacecraft is not anymore collecting data. The spacecraft has been among us for quite a while. The launch was in March 7, 2009, if I remember. And I do remember very well the year 2009, when we have an army of researchers at the Institute and at NASA Ames working on the data, working on the pipeline, and preparing for the launch. And I do remember the faces of my colleagues when we get the first light, the first image of this taken by the spacecraft of this patch of the sky located nearby the Cygnus constellation. I mean, this mission has been among us for quite a while, and this mission brought a lot of amazing discovery. One of the main discoveries, of course, is the fact that thanks to Kepler, we know that our galaxy has, in average, the stars in our galaxy have, in average, 2 planets in orbit around them. And a large amount of those planets could have liquid water. So this is very a paradigm shift into the perception of a galaxy, and that's one of the reasons we really wanted to have a special talk on this mission. So for that, instead of having me talking about it, since I'm not been involved, I'm not the right person, of course, we invited this researcher who have been intimately related to Kepler. The first one is Nathalie Battaglia. Nathalie is now a professor at UC Santa Cruz. She was an astrophysicist at NASA Ames Research Center, and she's been involved as a project scientist in the Kepler mission. She holds a bachelor degree in physics from the University of California at Berkeley, and a doctoral degree in astrophysics from UC Santa Cruz. So Nathalie did most of the career as a student in California. She moved to Rio de Janeiro in Brazil, but then came back to California in 1999, where she got inspired by this amazing mission project called Kepler. She joined the team led by Bill Borucki at NASA Ames, and she's been working on this mission since then. She led the analysis that yielded to the discovery of 2011 of Kepler 10b. I think you're going to talk about that. And the first confirmation of a rocky planet outside our solar system. So the second researcher is someone I've been working for quite a while now, is Doug Cadwell. Doug is a SETI Institute scientist, co-investigator on the Kepler mission, and instrument scientist for the Kepler mission as well. So Doug is an expert at the most successful techniques for finding small worlds around planetary system, looking those worlds by transit. I discovered recently that Doug has not been always living on the North American continent. He also lived for a while in the South Pole, where he's conducting various observations over there in Antarctica. Doug is the instrument Kepler scientist is an instrument scientist for the Kepler mission. He's also involved in various other missions, such as K2 and TESS as well. So please join me in welcoming Nathalie and Doug. They're going to give us a play today. They're going to have different small talks, and hopefully we're going to have time for discussion as well. Thank you very much for joining us.
I guess, okay, sorry, we're not very rehearsed here. So we're going to have a panel discussion as well, like a moderated discussion. So Doug and I have some slides to share. Doug's going to talk a little bit about the history of Kepler and how it came together, and we're both going to share some science results. Mine with regards to the exoplanets that Kepler discovered. Doug's going to talk a little bit about that too, but also some of the stellar astrophysics, what we learned about stars. So we're going to go back and forth, so I'm trying to figure out what the best thing to do is. Maybe I'm just going to hang out on the stairs here while Doug takes his turn.
Okay, well, welcome everybody. as Natalie said, we'll be going back and forth. So Frank mentioned that as of October 30th, 2018, NASA declared the official end to spacecraft operations for Kepler. And it was a sad day, but we really knew it was coming. It's been running out of fuel for quite some time, and it wasn't a surprise. In fact, it was a surprise that we got so long. We were told by engineers at Ball starting a year and a half ago that we'd be lucky to get 6 more months, and we heard that every 6 months for sort of a year and a half. So they did a great job really getting the last bits out of it. The NASA put together a Kepler by the numbers slide, and some of the key things here I think are that we were in space for 9.5 years, 9.6 years. We really completed 2 different missions. We did the Kepler Prime mission, which was the original goal, and then when the spacecraft had some problems, we were able to essentially reinvent a new mission and do continue great exoplanet science, but also do a lot of new science. We observed over 530,000 stars, something like 190,000 of them in the Prime Kepler mission, and the rest in various K2 campaigns. Probably the most important thing, or most exciting thing to me, and I think Natalie, is we've discovered over 2,600 confirmed exoplanets. There are something like 3,800 known confirmed planets from all different techniques, and Kepler has found about 70% of them. So that's a pretty good accomplishment. And at the end, the spacecraft is orbiting the sun, so it's trailing behind the Earth. It's about 94 million miles away. It's 1 AU. It's the distance that the Earth is from the sun, away from the Earth. So it's been getting very hard to communicate with, and it's getting old. And we were sad, but not surprised to see it go. And I think this is, for Natalie and I, who started on Kepler, 10 years before launch, it's great to be here and have seen it through. And I think we really have something to show for this work, not just us, but all the people who worked on this. And it's pretty exciting that it's done so much, and I think more than any of us expected, probably. So I want to talk a little bit about how we got here. Kepler's this awesome NASA mission, but it didn't start out quite so glorious. Natalie and I both started working for the principal investigator, Bill Barucki, on a test bed for Kepler, which we called Vulcan. And this was a small telescope. You can see it up there. It was a Canon sports lens that we put in a telescope. And it was at Lick Observatory up above San Jose. We had a little tiny dome that Bill basically had to do a lot of construction on to get it even habitable. Had to fix the roof, put in a floor. And the version you're seeing there in the bottom is kind of like version 3. That's the premier version of Vulcan right there. We've got it fully automated. We've got an automated rain shield, the green corrugated plastic that goes over the telescope when the dome closes, because the dome leaks, and if we don't have that, then water drips on the telescope. You can see, the most important thing, our Orchard Supply hardware paint bucket was our calibration light source, so we could take flat field images to calibrate the CCD camera every night. And the picture there is of Fred Witteborn, who was also a NASA scientist who spent years working on real missions, but also was great at going up there and fixing things that would break, and he helped us a lot. There's sort of a close-up of the camera there. You can see the main camera. Oops, I blew it. The main camera is here. We had a guiding scope. And we also had a lot of problems with this dome, not the least of which was our little friend Spock here, whose family moved into our automated weather station and chewed up a lot of the wires in the PC and caused us to have lots of problems keeping the thing running. But it worked in that it taught us a lot about what we needed to do and the kinds of problems we would run into when trying to analyze this data. A lot of the data analysis algorithms that we use on Kepler were developed to work on Vulcan and were improved, but based really strongly on what we did for Vulcan. So upgrade slightly once NASA gets involved and we get more money and the proposal finally gets reviewed, it gets approved. We've got the Kepler mission before launch, and you've probably seen some of these pictures. On the left here is the focal plane. There are 21 science CCDs, charge coupled devices, digital cameras. They're laid out in this focal plane that's about, you can tell how big it is because that person, it's about this big. And the telescope is mounted here inside the Delta II before launch. The solar panels here, the spacecraft and radios here, and this is the coupler to the top of the rocket. So that part from there up is Kepler. So we'd spent, again, something like 10 years, Natalie and I, and a bunch of other people working on this to get to this point where we put it in a rocket, and on, as Frank mentioned, on March 6th, depending on when you count in UT or local time, we launched from Florida, and it was a beautiful launch. It was a night launch. We were there. I think Joe was there probably. And it was a spectacular event. A great cause of celebration. I mean, we'd spent a lot of time working on all sorts of things to get this thing to launch and work, and it didn't blow up, and that was very exciting. And the principal investigator, Bill Baruchi's in the front there, the deputy principal investigator, Dave Koch, in the back, celebrating, and there's Natalie, and there's me. So we actually were there too. We made it to the launch, and we were all celebrating. It was a great time, and it launched, it worked, and now it was time to get to work. All the stuff we'd done was kind of leading up to this. Now we really have to work. And so, as Frank mentioned, we got our first light image. You can see the structure of the focal plane there, images from each of the CCDs. It's a big field of view. It's about a hand's width in the sky, so it's much bigger than a lot of telescopes like Hubble. And in this field of view, we were monitoring about 170,000 stars to look for planets in Kepler. So the first light, we saw this image not long after launch, and it worked. All the cameras worked. We could downlink the data, and so we were very excited. And we started as part of commissioning or part of the checkout of the mission to analyze, to take a little bit of data that we were going to collect as in real science mode. And we took 10 days of data during commissioning, and one of the stars in there was this star called HAT P7, which was a known extrasolar planet that had been discovered from the ground. And so we knew we had a planet in there that was transiting, and we wanted to see what the Kepler data looked like. And I think this was the moment that all of us who were working on it, when we saw this data, really realized that this thing really was going to work, and it was really going to do what we wanted. The graphic here is a plot of I forgot to mention what we're actually doing. What we're doing with Kepler, in case you don't know, is we're looking for planets that transit or pass in front of their star. So the star is shining brightly. The planet is a dark spot, and if it passes in front of it, it blocks some of the light. And the brightness we measure of the star gets a little bit dimmer, and the amount dimmer it gets is basically the size of the planet. So what we see here is a plot from the data of the discovery of this transiting planet. It's about the size of Jupiter, taken from the ground. And all these little points are measurements of the brightness of the star. And then when the planet goes in front of the star, all the little points get a little bit dimmer. And so that black line is a model for the transit of this planet, and it was a known transiting planet. And our 10 days of data on Kepler were this. And that's the data. That's not a line. That's not a model. That's the Kepler data. And when we saw that, we were like, this is it. Why, throw away all the ground-based things like Vulcan. They're obsolete. And so if you zoom in on this plot, you can see 2 times you get a really clear, beautiful picture of the primary transit going. And you start to notice this little weird thing halfway in between the 2 transits that we measured. As this planet goes around in a very short orbit of something like 4 days around its star. And when you zoom in a little bit more, you can see there's another little dip when the planet goes behind the star. So we were actually seeing light from the planet that goes away when the planet hides behind the star, as seen by Kepler. And the depth of that change in brightness there is about the same as the depth of an Earth transit around the sun. And so you could see that in the data. This was with very minimal processing, and we knew then that this is it. This Kepler is going to be able to do what we want it to do, which is to find other Earths. So I'll let Natalie take it away. Tell us what it actually did find.
Hello, everybody. This is, NASA recently announced the end of an era. This is the end of an era, and this is the first talk I'm giving where I will be referring to Kepler in the past tense, which feels very strange. As Doug said, this has been our entire career for more than 18 years. For Doug, probably 20. So we started on this mission before it was a mission. So from conception, proposal writing, all the way through the construction and the analysis of the data. People ask me, well, so how are you feeling about this? I mean, to have experienced this, to have lived it, all these amazing moments that we shared. You know, the science is fantastic, but the sense of camaraderie and teamwork and shared purpose and all of that, just experiencing, I think, the greatest qualities of what it is to be human. That's what I got from Kepler. So how am I feeling now that this 20 years is over? And I can say quite honestly that I am not feeling a drop of sadness. And that's because we accomplished everything we set out to do and more. And that's a really great feeling. So I'm happy to be here to share with you some of the highlights from the mission and hopefully to have a nice informal discussion so you guys can ask a lot of questions. But the story starts here on the eve of Kepler's launch in 2009. You know, I was fortunate enough to have a front row seat to exoplanet discoveries, starting with the very first one. I was a graduate student when the very first exoplanet discovery was announced, and it happened in Florence, Italy. And I serendipitously happened to be able to go to this conference only because my advisor, who was actually invited, couldn't go. So they sent the grad student instead. And nobody knew that this was going to happen. And they did it on the very last day of the conference, you know, Friday afternoon when everybody's looking forward to going home. That's when they made the announcement. And I didn't really appreciate at that time how it was going to change the course of my life. All of us at that time, there was no such thing as an exoplanet scientist. We were all stellar astrophysicists because the way that we found planets was by inferring their existence based on something weird about the star itself. And as Doug explained for Kepler, that means measuring the brightnesses of stars and looking for these eclipse events or shadows that are being cast out into the galaxy that sweep across the face of the telescope. So fast forward now to 2009. That first discovery was in 1995. Fast forward now to 2009. This is what the scene looked like on the eve of Kepler's launch. Every point you see here is a discovery of an exoplanet that had been made mostly from ground-based telescopes. There was one European mission called Corot that was launched before Kepler, so some of those points are from Corot. The points are colored by the technique with which the planets were found. Doug described the transit method, and those points are colored pink on this diagram. The blue points were discoveries made with the Doppler technique, which we can talk about during the Q&A if you're interested. And there are horizontal lines there marking different planet sizes. So you can see that on the eve of Kepler's launch, over 85% of the discoveries were larger than Neptune, and there were about 300. So now fast forward even just 4 years. After 4 years, the scene changed quite dramatically, and now I'll add yellow points showing Kepler's discoveries. Kepler has added about 4,500 points to this diagram. As Doug said, about 2,600 or 2,700 have been confirmed or validated by other observations that corroborate the planet interpretation. But even of those remaining 2,500 or so, the reliability of that catalog is at the 90% level. So well over 90% of these dots are bona fide planets. And you see that the scene is quite different. Now over 85% of the discoveries known to humanity, the planets known to humanity, are actually smaller than Neptune. So you put a new piece of technology out into space and it opens your eyes to a reality that you didn't know existed before. And while we could have imagined that such planets were common in the galaxy because we all watched sci-fi and Star Trek, we grew up on Star Wars, it's quite a different matter to actually know, right? To imagine is one thing, but to know is very different. So there's a lot of information in this diagram that I don't have time to get into, but I do want to make a couple of highlights. First of all, Kepler has taught us that the diversity of planets in the galaxy far exceeds the diversity of planets in our solar system. we found all kinds of weird things that we didn't know existed. And here I'm showing not actual images of planets, but artists' renderings of planets as thumbnails, just to kind of articulate that, give you a feel for that diversity. Starting from the upper left-hand corner, we've got planets orbiting dead stars like white dwarfs. These are the embers of burnt-out stars. Also planets orbiting evolved giant stars. The next image, glowing yellow, is an artist's rendering of Kepler 10b. As a class, these are referred to as lava worlds. They orbit 20, 30 times closer to their star than Mercury does to our own sun. The star-facing side has temperatures in excess of that required to melt not just rock, but iron at standard temperature and pressure. So it's got an ocean, but larger than the Pacific Ocean, but not an ocean of water. It's an ocean of molten rock or lava. And if you take that to more of an extreme, you get the third thumbnail. You get cases where a planet is being bombarded by so much radiation that it is literally photodisintegrating in front of our eyes. And we know that that's happening because the signal, the way that the light from the star dims when this object comes into view, or comes in front of the star, has a very different shape because of this long cometary-like tail that causes the brightness to dim and then come up slowly as that tail sweeps across the face of the star. We have planets like the one depicted in blue at the bottom. These are things that are thought to be ocean worlds, planets that are about the size of Earth, but they seem to be enshrouded by a thick layer of hydrogen and helium and probably molecular water that is sequestering the very interesting rocky material down in the core from the interesting chemistry in the atmosphere, and probably precludes the existence of life, but we're not sure. We see planets orbiting not one but two stars. We call these circumbinary. So if you look at the sunrise and sunset, you would see not just one star, but two. And those two stars are gravitationally bound, so they swap places in the sky quite elegantly. And then finally, in the upper right, this is a planet that is orbiting a star in a gravitationally bound cluster of stars. Stars often form, most often form our galaxy in groups because they come from the same giant molecular cloud. And so those groups can be loosely but gravitationally bound. So if you are on a planet orbiting one of those stars and you look up into the sky, you're going to see a bejeweled sky quite different from what we see when we look up into our own. But planets orbiting stars like this give us a very interesting view of planets at all different ages. And Kepler has found planets that are just a few million years old, all the way up to planets, even rocky planets, that are the age of the galaxy itself. If I take the Kepler discoveries and I just make a bar graph of what their radii are, I get something like this. So I've got radius of the planet, or size, on the x-axis, and on the y-axis, I've got the fraction of planets observed in those different radius bins. And there's I've colored the bars to help guide your eye. So if a planet is in kind of the rocky domain, things we think of that are mostly Earth-size, I colored the bars brown. If they're giant planets like the gas and ice giants in our own solar system, Uranus, Neptune, Jupiter, Saturn, I colored the bars blue. And what you notice here is that the planet that is most common, most numerous, the most abundant planet known to humanity right now is literally the gray area in between, a kind of planet that we don't even have in our own solar system, that's kind of between the tiny rocky stuff and the big gas giant. And that represents a tremendous mystery to us because we don't know a lot about their compositional diversity or what they are because we don't have any examples. Now, Kepler is a demographics mission. You know, I talked about the end of an era. You know, having had this front row seat to exoplanet discovery since 1995, all the way up to the present time, I look back and I think of exoplanet exploration as kind of different eras. The first era, leading up to those 300 planets that I showed you in the previous scatter plots, that era was kind of like stamp collecting. You know, every discovery was celebrated. You know, it It was a press release. Every one planet that was discovered was a press release. And it did feel like a bit like stamp collecting. And then all of a sudden, the floodgates were open, and there's, thousands of planets. And that ushered in the epoch of exoplanet populations, studying the demographics of planets. Having a statistical sample of discoveries allows you to ask really big questions about planet formation, their frequency, their diversity, as you've seen already. So that was Kepler's reason for existence, right? Kepler was funded to determine the frequency of planets that are Earth-size and potentially habitable in the galaxy. So what we need to do then is to take this observed sample of discoveries, and we need to convert it into a measure of the actual population of planets in the galaxy. And that's not as easy as it sounds. There are lots of biases. For example, Doug described this transit method. In order for us to see a dimming of light, the planet has to go directly between the disk of the star and the telescope. That shadow has to sweep across the telescope. But stars in the galaxy are all oriented in different ways, and their orbital planes of their planets are oriented in all different ways. So for every one that we see, there are something like 10 to 100 or 200 that we didn't see simply because the geometry wasn't right. So in order to get a measure of the intrinsic population, we have to make these kinds of corrections. And so I'm going to do that for this bar graph, and I get something that looks like this if I plot it from 1 Earth radius out to about Jupiter size, or twice the size of Jupiter. And so what you notice is the brown bar went up a lot compared to the gray bars, and the blue bars actually went down. So this graphic told us right out the gate, very early, I think something like in 2011, just a couple years after launch, it told us already that small planets in the galaxy, at least orbiting from 1 astronomical unit inward, small planets are significantly more common than ice and gas giants. And the other thing that's really cool about this plot is if you look at the y-axis, that's the average number of planets per star. So for that brown bar, it reaches up to about 0.4. So 40%, on average, 40% of stars have such sized planets, right? Now, if you add up those numbers for every bar, 0.4 plus 0.3 plus 0.3 plus 0.15, you quickly get to a number larger than 1. And what that is telling us is that, on average, every sun-like star has at least 1 planet. And that little factoid changed the way I see the night sky in a very fundamental way. And I think Kepler has done that, not just for me, but for humanity in general. So now we can also ask ourselves a question, well, what does that mean about potentially habitable worlds? And the way that I'd like to communicate this to you is with a thought experiment. Let's take the Milky Way galaxy and let's shrink it down to the size of the continental United States. Okay, so we're here in California, very close to the Pacific Ocean, right? So you can imagine us here in Menlo Park, our back to the Pacific Ocean, and we look across the continent and we say, okay, where is the nearest potentially habitable planet, Earth-sized planet, likely to be, based on Kepler statistics? And the answer, it turns out to be, is right here on the corner of El Camino in Ravenswood, like at this local pizza place. It's very close. In fact, that's too far by about 30%. It's about 1/4 of a mile in this thought experiment, or within 10 light years on galactic scales. And that also changed our perspective in a very fundamental way. It catalyzed the search for life, not just within NASA as an agency, but across the globe, so much so that Congress in 2017, through the Space Authorization Act, added a 10th objective to NASA, our space agency. You can imagine the kinds of things that NASA's tasked to do. Number 10 is now to search or understand the distribution of life in the galaxy. And that's largely in part because of these results. So I'm going to pass the baton back over to Doug.
Cool. So we've talked about some of the great things Kepler's done. The Kepler mission, most of these results came from the Kepler original mission. I mentioned early on that there were some problems with the original spacecraft, and in May of 2013, there was a failure of one of the reaction wheels that controls the pointing that kept us from staring at the spot in the sky where we found all these great planets from. So this was kind of sad at the time. We thought it was sort of an early. We were hoping to go longer, but with a lot of work and some amazing ideas in engineering, we were basically able to turn these lemons into lemonade and come up with a new mission. And the engineers at Ball realized that even though we couldn't point where Kepler was originally pointed in Cygnus, by pointing the telescope in a way such that the sun shining on the solar panels tended not to make it roll, we could stare pretty stably at a bunch of different fields for about 90 days each. So that's still pretty long. It's not 4 years, but it lets us look into new places. The limitation was we had to look in the plane of the orbit of Kepler. So that's the ecliptic plane of the Earth's orbit also. And what that meant is we would stare at one spot for about 90 days and then move to a new pointing. And that mission was dubbed K2, as the follow-on to Kepler. And it went on for a little bit longer than the original Kepler mission. That's what we just completed now, was K2. And it added a whole bunch of new exoplanet discoveries, but also enabled a lot of new science. In the Kepler field of view, we carefully chose the field to be sort of optimized for what we wanted to look for: planets, sun-like stars that would allow us to see exoplanets. But K2 was sort of forced to look all around the sky, and so we got a lot of serendipitous astrophysics. And I'll just mention two what I think are pretty interesting results. One is, and Kepler did a lot of this too, is the study of stellar structure. The field is called asteroseismology, and the way it works is stars are these big balls of gas, and it's like a big liquid ball of gas, and it's oscillating. And there's a picture here of some of the oscillations you can see, and what that means is the ball is expanding and it's quivering, and when you look at the star, it's changing size and temperature, and what that means is its brightness is also changing. So if you stare at it with something like Kepler, you see these changes in brightness, and they're periodic, and they depend on what the star is doing. And I've got some plots at the bottom, which I won't explain, but they're basically a power spectrum of the star. So they're the frequencies for a given star. And it turns out that these frequencies tell you about the structure of the star, not just the surface, but the interior. And so this astroseismology is really a way to use the change in brightness of a star to understand what's going on deep inside the star, where we can't see anything. We don't have a direct way to measure it. And two exciting discoveries that came out of this were we were able to see that the cores of some of these stars were rotating much faster than the envelope, the part you can see. We can measure with Kepler the rotation of the envelope, the part where all the light's coming from, relatively easily. But what we found with astroseismology was that the frequencies that were coming from the core told us that the core was spinning much faster than the envelope. So there were stars that had distinct layers of different structure inside them. A related thing that we learned was that as stars age, they start out mostly as hydrogen, they burn the hydrogen, it turns into helium, and they're not quite hot enough for the helium to start undergoing fusion, and you get a shell of hydrogen on the outside of the helium core that's burning. And as they do this, the star starts to expand, and it becomes a red giant. This will happen to our star. We have like 4 billion years more, so we're okay for now. But it'll expand, and then it gets hot enough that the helium starts to undergo fusion. And one of the problems in astrophysics for a long time has been that looking at the outside of the star, the size and temperature is basically the same in these two different phases where the interior is very different. But by studying the frequencies of these oscillations of these stars, we're able to discern whether the star was just burning hydrogen on the shell or whether the helium phase had actually started. And that tells you the difference in age of these two stars and really helped us understand better the evolution of stars as they, like our sun, as they as they age and come off their main lifetime. So there's a bunch of more examples. There was a great talk early on in Kepler from one of the astroseismologists on the team, and he showed sort of page after page of new results. He's, this has never been seen before. This has never been seen before. This has never been seen before. Flip. This, and it was amazing to see the stuff that something like Kepler, where you sit in this relatively boring way and stare at stars, lets you uncover. One of the other things that staring at stars lets us do is we're looking at a lot of stars, and a very small fraction of these stars happens to go supernova every once in a while. And generally, there are a lot of supernova searches that are being carried out around the globe, and they find lots of supernovae every year. But they always find them at the peak of their brightness, because you don't notice it until you see a really bright object in the sky. But what Kepler has let us do, and K2 has continued this with some specific specific campaigns pointed in regions where we would expect supernova with lots of galaxies in the background, is let us be staring at these fields when a supernova goes off. So the people who are doing supernova surveys see, oh, there's a really bright supernova there, and then at the end of our 90 days, we download the light curves from K2, and we've got the brightness of that star before the supernova ever went off. And what we see here in this plot is, this is time. Here's a star, very dim, we basically don't see it. This is when it's detected from the ground. But what we see with K2 is, well, the brightness actually increased here from 0, and there's this little bump. And the little bump corresponds to when these kinds of stars go supernova, their core, their interior, suddenly collapses very fast when the fusion is no longer able to support it. And it happens so fast that the outer shell suddenly has nothing to stand on, and it starts collapsing. But as it's collapsing, the interior has now collapsed and exploded, and it's coming back out. And what we see in this little blip of brightness, which is actually a huge explosion, is this breakout of this shock wave coming out of the core, passing through the stuff that's still infalling. And then the whole thing starts going really bright, and this is when they're normally detected. So K2, by staring at a field before the supernova goes off, we've been able to understand much better the really early stages of supernovae. And some of the ones that have been detected don't have this breakout, this shock breakout, and people are trying to understand, why don't we see it in this supernova, but we do in this? So it's an ongoing study that we don't know the answer to yet. So those are two examples. There are many more, too many more to go into. What we've got a list of exoplanets. Natalie mentioned we've got the demographics of exoplanets. We have a pretty good understanding of the numbers and types of exoplanets that are out there. What we really want to do now is understand more in detail about these planets. What are they made of? What are their structures? Do they have atmospheres? And one of the ways we're going to do that is to try and see planets that are nearby, where we can make much more direct measurements of them. But Kepler found most of its planets in this one field of view in Cygnus, and they tend to be fairly far away around stars that are relatively dim, so they're hard to follow up. What the next mission that NASA is working on is called TESS, which is Transiting Exoplanet Survey Satellite. It was launched in April of this year, and it started taking science observations in July 25th, I believe. And TESS's goal is to basically map the sky, do an all-sky survey, and look for the nearest transiting exoplanets that we can then use other big missions to follow up and understand better. TESS is a smaller telescope, but it's got a much bigger field of view, and it scans a large segment of the sky for about 30 days and then moves to the next segment. And in a year, it'll do one hemisphere. It's starting with the southern hemisphere, and then it'll turn upside down or right side up, depending on your point of view, and do the northern hemisphere. And so at the end of 2 years, it will have surveyed most of the sky. And you can see in the picture up there in the upper right, the Kepler pointings that sort of cross shape with the Kepler field of view up in the northern hemisphere, and then the K2 pointings around the ecliptic, and TESS is going to fill in the rest. And what it will do is we'll find targets that hopefully will let us understand a lot more details about what exoplanets are made of, and I'll let Natalie finish out and talk about that. Do you want to just go? Okay. You sure? Okay.
All right.
We talked.
Just a couple words about why these transiting planets are so important. When you have this very special geometry and a planet is passing in front of its star, the starlight is going to pass, some of the starlight's going to filter through the atmosphere that hugs the planet. And that atmosphere is going to put a chemical fingerprint on the light that's headed to your telescope. So if you could catch that light that's passing through that atmosphere, spread that light out into a spectrum, now you can see all the chemical fingerprints of that atmosphere. So that's what we want to do in the future with tools like the James Webb Space Telescope, which is going to launch in 2021, and the 30-meter class ground-based telescopes like the TMT, the 30-meter telescope, very creative acronym, or the GMT, which I think is the Giant Magellan Telescope. One in the northern hemisphere, one in the southern hemisphere. They're both under construction. TMT was supposed to be constructed in Hawaii atop Mauna Kea. That was under litigation for a long time because of political reasons, but the Supreme Court of Hawaii just ruled in favor of the construction of the telescope, so I think that's going to go forward. With these tools, we are going to be able to do exactly what I just described. Here, these squiggly white lines, this is the spectrum. It's a measure of the energy that you get out at all the different colors. And all of these features going up and down tell you something about the constituents of the atmosphere, like greenhouse gases. So this is what you would see from that starlight filtering through an atmosphere if you just were right there. This is what we see from a telescope like Hubble. We have this tiny little region where we can look for features between like 1 and 1.5 microns, which is a measure of wavelength. And this is what we're going to see with James Webb, all those pink points. So it's going to open up the spectrum. We're going to be able to see lots of chemical diagnostics at much higher resolution and with much higher precision. The two diagrams I just showed you, one was observing like 10 transits, and the next diagram with James Webb was doing the same thing, even better, with only one transit. So this is the kind of thing that we're looking forward to in the future. With Webb, we probably won't be able to see features like oxygen that would be a telltale sign, perhaps, of a living world. But that day is on the horizon, and we know exactly how to get there. We know the kinds of instruments that we need to build, to the point where in NASA's 30-year roadmap, this quote was written several years ago, actually, before Kepler finished. Is there life on other worlds? For the first time in human history, we have finally been able to embark on the systematic scientific pursuit of an answer. We know how to get there, and I think that's the biggest legacy that Kepler could leave, is catalyzing that search for life in a very tangible way. So I think I'll end there, and we can have some discussion.
Okay, so we're gonna have a short discussion, and I think we're gonna take questions from you, from the audience, because you know my questions. Most of them we already talked before, right? So if you have questions, please line up over there. There is a microphone, and while you're walking there, I'm just gonna mention briefly that we said that the Kepler spacecraft is over, but in fact the mission is still continuing, right? Could you explain to us what's going to happen for the next 6 months, 9 months?
Yeah, so this is probably secret, but I don't know if anyone's in the room. So Kepler is still actually working, but we're going to send the command up to turn it off probably sometime on Thursday. So that's a contact with ESN. That'll stop the spacecraft operations. But we've still got a bunch of data from K2, and we're doing a reprocessing of all the data, all those campaigns collected for K2, and posting them to the archive so the public, anyone in the world, can see the data and see the results. And so we're going through that process, and we expect that to take about another year to finish doing a full reprocessing with all the best knowledge of our understanding of the data.
And I have a question for you, Natalie, before the audience takeover. So you basically described this amazing figure with all the diversity of exoplanets that's been discovered with Kepler. There is still some data to process. There is still some KOI, Kepler object of interest. Do you think we're going to find something else with this KOI, or do you think TESS will find something even we did not expect, more than what you show, like binary planets, like exomoons? Is there anything like this that you expect to see with those new instruments?
That's a good question. So are there surprises left? I think that there are surprises still left in the Kepler data as well. The Kepler data is the first 4 years of Kepler is very unique. I don't think that we're going to have another 4-year time, continuous set of observations like Kepler, in the foreseeable future. Of course, TESS is going to find surprises. I can't predict what that's going to be. And I'm faltering, I'm pausing because TESS is staring at a patch of sky for about 27 days and then moves. But yet at the very pole, it has overlap. So that region is going to be observed for a full year. But then it flips and it does the southern hemisphere. But I think what TESS has that's unique, it can survive longer. So we think that TESS can survive at least 10 years, and I've heard people say much, much longer estimates. So I think that it could potentially just kind of observe one hemisphere for a year, flip and do the other hemisphere, maybe come back and do, just keep repeating that. So if you can do that for 10, 20 years, then who knows what you'll find. Then I think that there could be some really interesting surprises. And of course, what TESS is going to yield are these very nearby planets that we can characterize using Webb and other telescopes. So that's going to be tremendously valuable.
Okay. Yeah. We already have questions here, so go ahead, please.
Thank you. You mentioned that most of the data is from transits, brightness variation due to transit, but then the initial slide that you shared also talked about radial velocity method. Could you just talk a little bit about that method? What is the radial velocity method?
The radial velocity method is a dynamical method. So Kepler, by looking at the dimmings of light, it tells us the radius of the planet. The bigger the planet, the more light is blocked, the more dimming you get. So we get the radius. The Doppler technique is actually observing the star, collecting the light, spreading it out into a spectrum, and seeing features in that spectrum wobble back and forth. And that wobble is indicative of the star moving. So the idea is that you all know that planets orbit their stars, but you might not know that stars also orbit their planets. And in fact, the two are orbiting about their common center of mass. If you could imagine a big star and a tiny planet connected by a rod, and you put your finger there to balance it, it would be very close to the star. And that's the point about which the star orbits, wobbles back and forth. Meanwhile, the planet, of course, has to traverse a large distance and accelerates quite a bit more. So if you can measure that tiny motion around the center of mass, then that gives you a direct measure of how, what's torquing it around that little planet. Another analogy would be like ice skating. If you've ever ice skated with a partner and you go out into the middle of the ice and you start to go, you crisscross hands and you start to spin in a circle. If you are a lot heavier than the person you're holding hands with, you're basically going to stay still and the kid is going to go whizzing around you. This is a similar idea. But that gives you the mass because it's related to the gravitational force. The two together are a power duo. If you have both the mass and the radius, you can calculate mass per unit volume, which is bulk density. Now you can say something about composition, and that's really valuable.
Go ahead.
Is Kepler in a relatively safe orbit? Do you imagine a day that it'll be captured and brought back and put in the Smithsonian or somewhere?
Yeah, we hope so. That Bill Barucki, the PI, that's the one thing he's still strongly pushing for. It's orbiting the sun, so it's in a 372-day orbit, so it drops behind the Earth about a week a year, which means in 52 years after launch, we're going to basically catch up to it. So it'll be, it doesn't ever come in the first few passes at least closer than sort of 1 million miles. But by then, we have till, 2062 or something to figure out how to go get it. So we should.
I think we could.
Enough time.
Yeah.
We could start a competition.
Maybe
prize.
Elon will go get it for us.
And it's.
I hope I live that long. Literally, I do hope I live that long. One of the factors of the Drake equation is the probability that a planet's in the Goldilocks zone, both in terms of how far it is from its star in the right temperate region, but also, of course, the size being somewhere in a reasonable range for life to evolve. Does Kepler give us enough information to have some approximation or at least error, some range of that number at this point?
Yeah, that number right now is about 0.23, 0.24, somewhere around there. But I think one of the interesting things that I've learned from Kepler is that even small planets have a compositional diversity. There's growing evidence that small planets have a compositional diversity. So that means that you can have a planet about the size of Earth that actually has a sizable hydrogen-helium envelope. Again, that might be sequestering away the heavy elements that create complexity. So I'm not convinced that it's true that every Earth-sized planet is potentially habitable. But we're very much beginning that line of exploration.
Thank you.
Basically, the transit method that you described will be very useful to characterize the atmosphere of those planets that transit and be able to understand the composition of the atmosphere. And from this, maybe infer as well the presence of biology on the surface of the planet.
I mean, this evidence of compositional diversity comes from the bulk density, right? So that's kind of this global measure of how compact something is. Webb and future telescopes will do more of a top-down approach, looking at the atmosphere, so what's being outgassed, and that, again, will tell us something. We'll be able to tie the two and see how they relate.
So we do need James Webb Space Telescope.
Yeah, I don't want to position Webb as a telescope that's capable of finding life. That's not what it was designed to do, but I think that Webb's greatest legacy will be determining the diversity of atmospheres of planets that are kind of like Neptune-ish or like this gray area in between that I described. I think we might learn something about what those are made out of, and that's going to be very important.
So this might be counterintuitive, but does it make more sense, even though we know like life exists on a star like the sun, which peaks, its black body peaks in like the visible spectrum, but if we looked at colder stars which peak in like the infrared, would that be more probable for life because there'd be less ionizing radiation and life could get started? You might have, if they were closer into their star in a Goldilocks zone around the planet, but around the star, but still like cooler. But it's just red light. It would be a darker, more dimmer sun, but would still have the ability to maybe have life evolve.
Great question. So stars come in different masses, and the most numerous type of star in our galaxy are these red dwarfs that he's describing. But it's not true that they're benign environments. These cool dwarfs are highly convective, and what creates magnetic fields on stars is the interplay between rotation and these convective currents in the envelope. And these stars have that in spades. So they actually have a lot of magnetic structure, which produces active regions like sunspots and flares and coronal mass ejections, and just a general large amount of X-ray and ultraviolet flux, which is not great for life. Although we think that that was important for kickstarting life.
Their evolution could be even faster than ours, right?
Yeah, exactly. So, evolution requires mutations, and that kind of radiation produces mutations on a faster time scale. So the cool thing, though, about the M-type stars, they're called M-type stars, these red dwarfs, the cool thing about them is that they live for trillions of years, not just billions. So it's very compelling to think about how life might evolve on a star given 1 trillion years to do its thing. So I'm really enamored of this idea that the heyday of life in the galaxy might be in the future, not now, because of these M-type stars.
Hi, so the public's fascination with space seems to wax and wane over time, and right now it seems to be at a high with the cultural impact of movies like Hidden Figures and Interstellar. What do you guys do to publicize the incredible scientific discoveries that you guys make? And do you guys work with media organizations to get the public a lot more excited about space in general?
The first thing we do is send Natalie out.
Well, all of us.
But
we all
we
talk
do.
a lot.
And NASA has a big public affairs group at all the NASA centers and who work with the missions. And we had some great public affairs people working with us on Kepler to help create some of these visuals and ideas of how to make this accessible and interesting. So.
Gosh, it's been so easy. This is not like selling, I don't know.
Car, selling a car.
I mean, this is so easy. Everybody is so enamored by this and is just hungry for information. I mean, from the beginning, I've always felt like the science is not about me. It's like we're doing this, like we're all in this together doing this exploration. You know, it's for humanity. And I've just, everywhere I go, I feel that so strongly. But one of the great things that I've experienced also is how Kepler and this science has inspired poetry, art, music even, lyricism. I mean, it's been so fortunate to see that. And when the artists get involved and they make these planets come alive, or they speak such eloquent phrases. One of my favorite quotes was from an essay contest that we had, and a gentleman in Portugal wrote an essay and submitted it. And at the end, he said, "One day from the shores of a new world, we will gaze out at the sea that took us there, and its waves will be stars." And that is just the eloquence of that, the poetry of it. It just taps into why we're doing this. So it's been really easy, but NASA is also very masterful at communicating to the public.
Yeah, I should mention that at the SETI Institute, we have an artist in residence program.
Yeah.
And one of the artists has been working on the sonidification of the Kepler discovery. And,
Turning Kepler science into sound.
into sound, yeah.
Yeah.
Hi. The actual examples of the exoplanets were really fascinating. I was wondering, like, there's a lot of news about like new exoplanets, also news about like the Tabby star. Do you have any other examples of really interesting or unique like exoplanets that you've found?
Planets or stars? Yeah,
both.
I mean, there's been all kinds of weird stuff. I mean, we could talk about heartbeat stars, a new class of stars called heartbeat stars. These are binary systems in very, very highly eccentric orbits. So these stars come in from far away, slowly, slowly speeding up, and whip around in their eccentric orbits. And when they whip around, there are huge tidal forces that cause the stars to ring. And so we see that in the brightness measurements. You mentioned Tabby star. These are stars like the Dipper stars that have all kinds of dimming events that are not strictly periodic like a planet, but due to circumstellar material that's maybe been broken up or smashed, maybe during an age of bombardment, and you have evidence of dust, circumstellar dust.
I think one we didn't really mention was there have been a number of systems of planets, not just one or two, or even 3 or 4, but there's eight stars we found with 8 planets very close into their star in a very flat orbit. All of them are transiting. There are a number of multiple planet detections, and so we've seen a lot of systems of planets that are much more sedate and aligned than our own. So that was an interesting find.
Yeah, I like to say, our solar system, the planets are all coplanar, kind of like a pancake. But in these systems where you've got 8 planets orbiting within like Venus's orbit in our own solar system, they're so flat that it's more like a crepe. It's just really, really exquisitely thin, which is puzzling. That's a new architecture, right? We're just beginning to learn how that comes about.
Thank you.
I'd like each of you to respond to this question if you could. If NASA gave you a do-over, apart from better reaction wheels,
that's the obvious answer, you know.
Well, true.
Oh,
What design feature would you most want to include in your do-over for Kepler?
But it was perfect.
I know. I've got one that's kind of boring, but kind of technical.
Go ahead.
And you can have lots of money.
Kepler had a the focal plane I showed there is very complicated and took a lot of work to put together. And while it was being built, we discovered some issues with the electronics that resulted in noise in the electronics, in particular channels on that focal plane. And so some of them are much noisier than others. And we know how to fix that, but at the time, the cost and risk of doing that, we decided were not worth trying. And actually, the guy who put the focal plane together said, you know, I have like a 50-50 chance of taking it apart and getting it back together working again. So what do you want me to do? And so I think what we could do is redesign the electronics, and in fact make them a little bit simpler now that we know more about it, and that would have made the noise that we see in some of these channels, which turns out to really plague us in the search for one-year Earth-sized planets, because of Kepler's approximately one-year orbit. That would have helped a lot. That's sort of a technical one. But
That's a really good one, because we would have found a lot more Goldilocks planet. Well, but the obvious one, I mean, you made it
You took
really
our good
easy
one,
when you
yeah.
said I could have more money. If I had more money, I would have put more fuel on board so the spacecraft would have lasted
3 gallons?
longer.
I mean, really?
Yeah, the whole
5?
9 years of operations was based on 3 gallons of hydrazine fuel.
Doug, is that problem you were describing, is that called jitter?
No, this was an electronic. We've called it like moire pattern or rolling
band.
There was some electronic parts that were oscillating at really high frequency, ringing, and we know what they were, and we know how they could have been replaced, and they just ended up putting noise in the data that
On time scales that mimicked transits.
yeah.
I see. Okay, thank you.
I have one, but my microphone is off. I think they don't want me to talk anymore. I wonder, will it be possible to have a filter wheel with a few colors to characterize some of those planets that we have no idea, the gray one? Having just a few indication on the color may be useful to indicate whether or not it's a mini Neptune or a true Earth-like exoplanet or super Earth.
We wouldn't have the precision to be able to characterize the color of the planet itself. What you can do with different colors is make sure that what you're seeing is not like sunspots or something like an activity signal.
And I would say, as mentioned, the one moving thing we had on Kepler broke. And part of the reason Kepler was, I think, so successful was its very simple design. It has no shutter, has very few moving parts, and adding more complexity probably would have made it more likely to break, would be my guess.
Hi. So the nearest star system is Alpha Centauri, right? So is it possible to detect any planet which is even closer, like a rogue planet which was orphaned from its star, and maybe do a star shot there?
Yeah. Well, I mean, you use the keyword starshot. I mean, so the breakthrough initiatives is putting money into that. But a couple things. One, we already know of a planet orbiting Proxima Centauri, which is one of the 3 stars in that star system. That planet was found with the radial velocity method. But there is another technique for finding planets that is going to become more and more important in the future. And that technique is called direct imaging. So this is more like what you imagine astronomy is, like in the cartoons, you know, an astronomer looking through a big telescope. The idea is to point a telescope out into the galaxy and actually image a planet, to see light bouncing off of a planet or being emitted by a planet. But in order to do that, you have to eliminate the bright glare of the star, because planets are really faint and they're hidden in the glare of the star. So in order to do that, you have to put up a thumb to block out the light so that you can see the faint things nearby. And that thumb is a piece of technology, either called a coronagraph or a starshade. And that technology is actively being developed. But there is a mission that's being proposed that's relatively inexpensive, where you could build a small version of that, put it into space exactly to do what you're saying, to find out if there are planets orbiting in the Goldilocks zone of the very nearest star. I personally think that this is an obvious thing to do, and it frustrates me that that it won't get funded. But it was proposed and it was rejected. Not that, I mean, Kepler was rejected 4 times, right? So this has only been rejected once, and I want to keep trying. But the biggest complaint is that there's a probability that we'll find nothing. But to me, that's an interesting answer, right? Let's find out if we have nearest neighbors or not, or at least put constraints on it. So we're going to keep trying.
And in this case, we will also have filters to characterize the planet, so we
Yeah.
have information on the planet itself,
That's
not only
right.
a pretty picture about
Exactly. Right.
We will know there is ocean, for instance, because if we're looking for invisible and UV.
Yeah, yeah.
Thank you.
All right, so I have two questions. The first one is a technical question for Natalie. So one of your slides, you showed a graph where you had the planets that had been discovered, or the exoplanets that had been discovered from Earth versus from Kepler. And it looked like a lot of the ones that had been discovered from Earth were much larger on average than the ones that had been discovered by Kepler. And I was wondering if you could explain why that is. And then the second question I had was whether there's any exoplanets in particular that either of you are really excited about that you think could be really good candidates for having life.
For having life? Okay. From the ground, we are limited in what we can see because we're observing light through the atmosphere. And you know this already because when you look up at the sky, you see twinkling stars. It's that twinkle. The twinkle is a change in brightness that you're observing because the light is passing through the atmosphere. And that precludes us from finding very tiny planets from the ground. It was necessary to put a piece of technology into space. Moreover, it was necessary to have a different technique for finding planets because with current technology, the Doppler or radial velocity method that I described before can't see planets like Earth. So it was necessary to have a new detection methodology and to put it into space. Once we did those two things, it's like all of a sudden you can see. So that's why, that explains the two diagrams. Kepler found a handful, a couple dozen, of Earth-sized planets, or planets smaller than about 50% the size of Earth or smaller, 80% the size of Earth or smaller, planets orbiting in the Goldilocks zone. They're all very, very interesting. But they're also relatively far away, so they're not great candidates for characterizing, and they're not going to be the places where we look for life in the future. That sample, you know, Kepler observed a slice of the galaxy going out to about 3,000 light years in order to do a demographic survey. Now we want to find all of the planets near us, and those are going to be the ones that we will characterize and look for life on.
Thank you.
Hi. First of all, I led a game called Kerbal Space Program, and your work was like very, very useful to us to develop the planets in the game. And you know, it was just incredible for me to listen to you today, so thank you. Second of all, my question was, what about the planets that are not in solar systems? How do we detect those?
Free-floating planets.
So, yeah, to date there have been some that have been found, and the technique that's been used is another one we didn't talk about, which is microlensing. And so this is a technique that uses the gravitational pull of the planet on the light that's passing by it from a background star to make the star, to brighten the star. So the light that normally we wouldn't have seen gets bent by the planet or the star and shines into our telescope. And so the background star appears brighter. And by watching it and seeing how that brightness changes with time, these microlensing events usually take of order a month or so. You can see, you can get an idea of the mass of this thing that's in between that you don't directly see. And there have been a few detections of these brightenings where the mass that was causing the brightening looked to be much smaller than a star. And those are what is proposed to be free-floating planets. And I think there's some question about the number of them. The problem is these events are very rare, and if you see one, that means there's probably a lot of them, and if you see two, that means they're everywhere. And so if you're kind of not quite sure about the second one, then your statistics of how many free-floating planets out there can be wildly varying. And I don't know the latest, greatest numbers.
I don't either.
Me either.
Yeah, but there are some that have been proposed.
It might be weird to think about the possibility of a planet just out in space not orbiting a star. How did it get there? But one thing that Kepler has taught us is that the formation of planetary systems is a very dynamic occurrence. Planets interact with the disk and with each other, and planets can actually get kicked out. They collide, and they can also get scattered and kicked out of the system, and that's what gives rise to these kinds of objects.
Okay, so before we close and finish this, I have a personal question for you too. Of each of you going to answer to this one. You spent a significant part of your life working on this Kepler mission. I mean, there's been joy and a moment of stress, I do know that. But now it's a new step in your life. You're basically going to start, you've really started something new because you moved to UC Santa Cruz, for instance. So what is going to challenge, because it's going to be the next big challenge in your life, in your scientific life? What do you want to see in your career now? What is the next big step for you? What's your dream?
Oh, goodness. I loved working at NASA. Working at NASA was my dream, and I've lived that and experienced that. And at this stage in my career, I felt that it was, that the way to leave a legacy behind is to move to academia and to do to carry on the legacy that Kepler started, which is catalyzing the search for life. So at Santa Cruz, I will be starting an astrobiology institute to search for life. More near term, I am leading the team that's going to take the very first exoplanet observations with the Webb telescope. We're going to observe 3 giant planets and create data or analyze data for the community to help the community to learn how to use this resource, which is the Webb telescope, as quickly as possible to leverage it and get the most science out of it. In terms of, Kepler has left me with some really nagging questions, and one of them I've already touched upon, which is this compositional diversity of small planets. I'm really curious about that because I think it's another term in the Drake equation that we didn't consider. So scientifically, I'm going to be looking at the planets that TESS finds. I'm going to be using the Keck 10-meter telescope in Hawaii to characterize them, and the future 30-meter telescope that is a partnership between the University of California and other institutes. Those instruments will give us the capability of starting to answer these questions. So I'm looking forward to doing that.
What about you, though? Well, I'm working on. I'm done. I'm working on tests somewhat. So I'm interested in helping them get their working get going and start collecting good data and trying to understand that and tie that into what K2 and Kepler have found. One of the things the TESS is going to do is find a lot more planets around these small M dwarfs, just because it's looking at a lot more. So it'll be interesting to compare that. One particular sort of related idea that I've been interested in for a while is this idea of what do planets with life look like, and I'm surprised still that we don't have a really good survey of what the Earth looks like seen from afar. And in particular, what does the spectrum, this infrared colors of the Earth look like over the cycle of a year with clouds and with seasons over multiple years? And so there's not a whole lot of data on that in the sense of the kinds of things James Webb will see, where it won't resolve the Earth. It won't see continents or forests. It'll just see the whole planet, and you'll get a spectrum. And I think there's a lot of very detailed models of those kinds of planets, but there's not a lot of kind of ground truth. So I've been interested in sort of thinking of a way, how can we put together just a really small instrument that would just go out somewhere and stare at the Earth for a year or 2 years and see how the colors of the Earth change with time.
Okay. Well, before you leave, I'm going to give you a beautiful present because you really deserve this. So this is as a token of our appreciation, to remember that you gave a talk here, the SETI talk.
Thank you.
This beautiful mug and a patch. Please put the patch on your bag. And please join me and to thank our speakers. Thank you very much for coming.
Thank you.
Thank you for coming.
Thanks, Natalie.